Too loud. As he moves the mic down. All right, let's start off with a quick poll. How many people here are responsible for BGP speaking routers or the security of BGP speaking routers? Okay, 20%. How many people here have read any of the vulnerability work, either the attack tree that we've published or any of the other BGP threats drafts that have been published? Okay, about the same amount. All right, what we're going to spend the next 90 minutes talking about is trying to put some real numbers and real testing behind some of the BGP FUD that's been out there. You've probably seen it in the papers, you've probably seen it on websites. BGP is completely insecure, the internet can be taken down in 15 minutes, we're all screwed, right? So we're going to try and talk about some real testing that we did, some tools we're going to be releasing today, nothing spectacular, but proof of concept stuff that allow you to reproduce a lot of the tests that we did. And we're going to detail a lot of this and try and not necessarily walk away saying BGP is fine and everything's great, but to point out that much of the vulnerabilities around BGP have to do with the platform they're running on rather than the protocol itself. So my name is Sean Convery. This is Matthew Franz. We're both in the Cisco's Critical Infrastructure Assurance Group, which is a group at Cisco that has no product responsibility. We're supposed to be completely vendor neutral, and our goal is to do forward-thinking research in the area of critical infrastructure, and that's a pretty nebulous definition, which could include, just about anything, which is good for our job security, I guess. So the approach we tried to take is the government expressed some interest in BGP security. I mean, Rob Thomas has said in the past, any of you know who Rob Thomas is, he's done a lot of work with ISP best practices. He says the internet runs on DNS, BGP, and caffeine. And you got to protect all three in order to keep the internet running. And so the focus of this paper, this presentation we're doing is focusing in on BGP. The government with the national strategy has identified BGP as a critical vulnerability that we need to address as a community to make this whole internet thing better. And so we're going to talk about some real testing in that space. We're going to talk through vulnerabilities, some testing we did on implementations, design vulnerabilities. We'll analyze the best practices that are out there because there's a whole list. If you go and look at Rob Thomas's hardening template or Cisco's BGP hardening template, there's this huge list of things you're supposed to do, many of which do really good things, many of which have a huge administrative burden and do okay things. So we'll talk about the best practices that stop the attacks that are most likely. And then we'll do some demos along the way. Okay, so when we started doing this, the first rule of any research is you do some kind of literature search to figure out what work's been done in the past. And we found a lot of work that I would call academic and theoretical in nature with respect to BGP vulnerabilities. These are a couple of the choicer quotes that we found during our search. And they have statements here that are more or less completely false, more or less true. Some of the better ones being that any outsider can inject believable BGP messages. Outside sources can break TCP connections by spoofing resets. A lot of these things that are claimed because there's an understanding in the IETF and in other standards bodies that, well, TCP, because it's not using IPsec or any kind of strong authentication or cryptography, is completely insecure, right? It's obviously better than UDP, but it's not something you want to rely on. So we found in the testing we did that security is not necessarily a black and white where you can say, all right, BGP is secure or insecure. It's really the trade-offs that you make, and this is probably old news to most of you. So the objectives that we had is we started out with an internet draft, or IETF draft that we published back in the fall, detailing an attack tree for BGP. How many people here have heard of attack trees, just in general? They're a pretty good way to look at threats. We're going to talk through some examples if you're not familiar with them, just so you can sort of get up to speed with the way we started approaching this problem. Because a lot of the assumptions were based around going through each individual field within BGP and saying, okay, well, this field can be exploited this way and this field can be exploited this other way. Well, instead, what the testing that we did basically tried to say is, all right, here's what a bad guy is going to try to do with BGP or do to BGP, and how can you try and stop those things? Again, we then went into looking at best practices and how those are going to sort of deal with the problem. I come from a network design background. Matt comes from a product testing, protocol testing background, so it was a good pairing to do this work. And then we wanted to say, all right, best practices are great, and we've had things that have been best practices for years that still nobody does, right? So what we wanted to say is, all right, how many people here are actually out there doing the best practices that we recommend? So to the extent we could, we went out on the internet and measured best practice implementation in ISPs, and this was sort of a non-voluntary survey of ISPs using tools that were written by our own Mike Schiffman, who's sitting down here. Wave, Mike. So Mike wrote some really cool tools, which due to the recent Cisco vulnerability, we're unable to release that particular tool because it's really bad timing. But the other tools, it's not really good to say, hey, we're releasing a tool that allows you to survey the complete internet. Why would you want to do that? I don't know. So this is what we'll talk through. Okay, so the methodology we went through. Lots of intro slides. Promise we'll get into the meat here soon. We wanted to look at the BGP-specific TCP attacks. Again, like I said earlier, a lot of the vulnerabilities that have been theorized around BGP have to do with attacking its transport. I spoof a reset message. I somehow spoof TCP to be able to send a BGP update. A lot of these kinds of things are all centered around TCP. Also, if you look at the implementations of BGP that are out there, many of them are tightly wedded to the TCP stack. So error conditions you can cause on the TCP stack will potentially flow over into causing problems to BGP. So that was one of the things we want to look at first. And that includes things like MD5 authentication, which we'll talk about, sequence number attacks, those sorts of things. Then we did some interesting work, which Matt's going to talk in more detail about, where we sent a series of malformed messages to a representative set of BGP implementations to try and look at the implementation vulnerabilities that might exist out there. We found lots of problems in the 50th exploit for Internet Explorer. We wanted to figure out, okay, what kinds of problems might be in deployed BGP speakers today. So that was one of the things we specifically set out to do. Again, then we took the BGP attack tree, which details all these attacks, and we tried to take that seed information from our TCP testing and our malformed message testing to try and formulate what attacks are the most successful for an attacker to launch, have the lowest entrance requirements, and have the highest impact. And that's really what should be solved first. There are two competing proposals right now to improve the security of BGP as a protocol. One is called SBGP, the other is called SOBGP. And they have pros and cons. But any replacement to BGP, because it's going to be a massive pain in the butt for large organizations and ISPs to roll this out, better solve a lot of these problems. So we wanted to try and do some work in this space, because again, it was actually pretty surprising to find out that, arguably, among the two most important protocols on the internet, we weren't able to find any systematic testing of implementations or designs using real tools and real test methods. This isn't certainly 100% in terms of the testing we did, but at least it's a start, because we weren't able to find anything. And then the active, or the non-voluntary survey that we did, we actually sent a single SYN packet on port 22, 23, and 80, which are the three command and control ports, SSH, Telnet, and Web, because even the most basic internet ISP administrator should know that he shouldn't allow command and control in from any arbitrary IP address. So if we figure if we were able to get a telnet session to somebody's router out there on the internet, then chances are all the more difficult to implement best practices, there's no way that they actually did those. So, and then we also looked at, will people respond to a TCP 179 connection, which is BGP? Can I send something on 179 and get a response? And if so, am I allowed to do some kind of fingerprinting to figure out what kind of BGP implementation it might be? How can I use that information, to potentially even cause some problems to that particular router? Okay, so most of the work, if you look at the three types of vulnerabilities, I'm not going to talk about those in any level of detail, but the three major ones, design, implementation, and misconfiguration, most of the theoretical work has been around design and misconfiguration. Very little work in implementation and trying to find flaws in implementations. So that was an area we focused on. Also, we spent some time in design. So all the flaws that we found, all the vendors have been notified. They've been given the tools necessary to reproduce the conditions that we found. The CERT has been given a set of test cases, which they have already distributed to all the BGP vendors that we didn't get a chance to test. No vendors that we tested or didn't test, no flaws that we found or didn't found are going to be disclosed in this talk, so please don't ask, because we don't want to get tripped up. All right, so here's a quick attack tree example taking something from the physical world. At the root of the attack tree, you can see the goal of the attacker. In this case, he's trying to gain unauthorized access to a building. So all the leaf nodes that are underneath that become the various methods that he's able to do that. So he can unlock the door, pick the lock, break the window, etc. And then for each one of these levels, you can further elaborate more sub-goals. Blue indicating, it's an or relationship. I can either social engineer to unlock the door with a key, or I can steal the key. Or an and condition, as in the case of trying to follow somebody in. If you're tailgating into a building, you probably need to be wearing the right clothes no matter what method you're choosing to do it. Something appropriate for the location. So this gives you kind of a way to think about flaws and vulnerabilities as they relate to what the attacker is going to actually do as opposed to what's theoretically possible. So in the attack tree that we link to at the end of this presentation, we talk about BGP attacks in the attack tree format. This is one of the attacks, in this case, resetting a BGP session. Well, I can either misconfigure a router or compromise a router to cause that connection to be reset, or I can send some kind of a message. And the easiest way to do that is to send a TCP reset, because in order to send any of the BGP messages, like a notify, an open, or a keep alive, I have to also get the TCP sequence number guessing right anyway. And if you've already gone that far, why not just send the TCP reset? Okay, so this is a summary of that draft, because as I found out in the poll, most of you haven't read it, and I certainly wouldn't have expected everybody to. What we did was we broke down atomic goals, which is what we called the lowest level of the tree. So these are sort of the building blocks of the larger attacks. So things like compromising the MD5 authentication, establishing an unauthorized session, or changing a path preference of a prefix. When you're talking BGP, essentially you're sending prefixes out between your peers to try and say, okay, I know how to get to these 20 networks, and this is the path you would use to get them, or here are the different preferences you might use. There's all kinds of different optional parameters you might send in those BGP updates. And then there's a bunch of attacks that really have nothing to do with BGP, which are more supporting attacks, things like compromising a router, denial of servicing a router, those kinds of things. And then you take those two and kind of smush them together, and you're able to do these larger attacks, things like, what would it take to try and disable significant portions of the internet, which is this attack that everybody's saying, because BGP is so insecure, it's so easy to do. So we tried to look at that. If you're interested more in that, I'd encourage you to take a look at the draft. Okay, so now I'm going to turn it over to Matt, who's going to start the conversation about the specific vulnerability testing that we did.
So attack trees can be kind of interesting. A couple of years ago, started using them for several protocols. So when I was doing testing of Cisco products, and they require a little bit of a change of how you're thinking, and they can lead a lot of, end up with a lot of arguments, and what's the best way to represent. You can get caught in this whole trap of being over formal. But I found them to be one of the more useful tools in terms of trying to be comprehensive, trying to anticipate all the attacks that a device or a protocol or an application will expect, and also prioritizing and determining, what are the specific preconditions that you have to do for an attack to succeed. So if you think of an attack tree as a tree, the leaves are tests that are specific things that either cause something to happen or they don't. So we took the work we did as part of the IETF and came up with a set of tests, and then we wrote tools, and this is basically what we came up with. So we started out with looking at TCP implementations of a variety of routers, because the primary belief was that TCP is insecure, therefore BGP is insecure. So, and a lot of these tests aren't necessarily the sexiest tests, but if you come from a background of in a product company of having to provide some level of assurance that your products aren't going to have vulnerabilities, and particularly if you're in a security test team, and kind of your greatest fear is that somebody's going to post a bug track the next day for a product that you tested, and that's no fun. So you basically come up with, you want to cover all your bases first, get the low-hanging fruit. So we start with the basic TCP things that are pretty well known. Then we developed some attack tools for MD5, for the authentication that BGP uses. Looked at some update flooding attacks. Flooding is common ways to exhaust memory, result in CPU exhaustion, things like that. And then also generate a variety of malformed messages. Protocol fuzzing is a popular technique. There was a big deal when this series of SNMP vulnerabilities that impacted nearly everybody's implementation. And there was this group in Finland that wrote a tool called Protos, and you're probably familiar with that. So basically, what we did was, and one of the neat things about this project was that typically when I did product testing, I'd maybe see one or two implementations, and given that a lot of the Cisco products, they'll just simply port the implementation from one platform to another. I really didn't see a variety of behavior. But this way, I got to see a lot of different stuff. And big surprise, given the ambiguity in the RFCs, there's a lot of wiggle room for vendors to do interesting things which can be exploited. So when we did our testing, we used pretty much the default out-of-the-box configuration. We didn't try to tighten them down in terms of adding any sort of access controls, for this initial base set of testing that I'm going to be talking about, or any sort of, filtering mechanisms. When you see test results in here, when possible, I try to include the number of implementations so you can get a sense of the range of responses that we get. And when we talk about, impact of certain flooding attacks, the CPU utilization and, impact of things like that, it's on a, we tried to build our network as representative as possible, but it's not a fully loaded network. So, like Sean said, one of the problems with some of the existing BGP vulnerability work is that there weren't any tests, there weren't any tools. So when we did our TCP and BGP testing, we used a variety of well-known packet construction tools that you're probably all familiar with: HPing, Nemesis, Netcat, a variety of things like that. But when we needed to do something new, we did write some tools to do that. So the MD5 password cracker, the generation of the TCP option 19 for the MD5 authentication, the hijacking tool, that's new. The fuzzing tool was something that I'll talk about a little bit later. That's basically a general purpose way to generate malformed messages for a wide variety of protocols. Some simple ways to just some Python scripts to generate opens and updates, basically just pretty much hacked together by looking at Ethereal and building the packets, putting the typical ASCII string stuff. And then the tools used for the ISP survey, those were new as well. So the fuzzing tool, we're not going to be able to release that. I'll talk a little bit more about that later. In the future, we'll probably be able to release the ISP tools. And these are available on the Cisco website. So one of the first question when you get exposed to a new protocol, and what you start thinking about is, what can I do and from where? So you need to prioritize the sorts of attacks that you want to test against the protocol. So typically you start with what can a remote blind attacker that basically knows what the target IP address is, and that's it. What can that attacker do? And you want to make sure that your protocol is resistant to those sorts of attacks. So typically you'll start with protocol negotiation, assuming zero knowledge, and in this case, SYN flooding would be the most obvious and well-known attack. Then you can go into TCP resource exhaustion acts later. Some of these are known as NAPA attacks. And then as you start to be able to send BGP messages such as open and update. So big surprise, quite a variety of response when you start probing BGP implementations. And from pretty tight that are very difficult to exploit to quite promiscuous. So the best case, I'm at home on my DSL, DSL modem, and I start trace routing across ISPs, and I start thinking, oh well, these are routers. Okay, I'll do a probe to port 23. Oh, I get a SYN-ACK back, so this must be a router. Now let's use HPing, send a 179, and oh, okay, wow, I actually get a SYN-ACK back. So that's not a good thing. In only one of the implementations that we tested, would it be silently dropped? So that's the recommended behavior. So there should be no way for me, I'm just any arbitrary IP address. I'm not a configured peer in the BGP configuration. There should be no way for me to just send that SYN and get a SYN-ACK back. But as you can see, that isn't the case for most of the testing. So the more typical response is, to get a reset ACK, which is basically looks like a closed port. So that's not so bad. The worst case is obviously to SYNACK that, because that's going to leave you susceptible to TCP resource exhaustion attacks, or allow you to go further along and start sending opens. So this next says, if I'm spoofing a SYN from a configured peer, the goal is to see what I get back. So there's an established BGP session, and I spoof it from the peer. The behavior is typically to either get a reset ACK, which is a good thing, because it shouldn't know, I mean, there's already a session established, so it should not attempt a SYNACK. But as you see on about 3 of the implementations, there was a SYNACK, so not a good thing. So moving on to BGP, let's say I send an open to a non-configured peer. And what I mean by non-configured peer is you're not explicitly identifying that IP address or the autonomous system number that matches up to it in the configuration. So in most of the cases, you get a reset. Okay, that's cool. On one implementation, you get an open notification back. Now, it was interesting when I started doing this a couple years ago. I noticed a few of these where I would actually get an open back. So, and then when Mike did the scanning of the internet, we found a whole lot of them. So there are some implementations that we haven't tested out there, and there are a relatively large number of BGP implementations that you can send opens to. You know, you could possibly send malformed opens to some of these, and who knows, maybe some of them might crash. So if you have an invalid AS, you get two different options back. Basically, an error authentication failure or a bad peer AS. So if you put all this together and you maybe use some TCP stack fingerprinting, you can probably determine the operating system. And then if you take application layer stuff from Telnet or HTTP or SSH version numbers, you know, the banners and the negotiation, you can probably determine what type of box it is. Okay, some of the interesting things that we ran across was, you know, you start sending all these opens. Some devices have, you know, 1 to 3 minute timeouts. So it made it kind of a pain in the butt when we were doing all these test cases, because we had to manually reset all the sessions. And then there was one really funky implementation that you basically use Netcat and hit a bunch of returns to port 179, and it sends a BGP open back to you. So we didn't try to exploit that, but there's some weird stuff out there. Okay, so y'all are probably familiar with SYN floods, been around for a long time. What I've found in testing various TCP applications is that, and this is not so much true with SYN floods, but when you start making connections go to the established state or some of the other states, the closing states, you can cause the application to crash or use up all the memory, and there's lots of interesting things to do. So we wanted to see if BGP had the same issues. So y'all are familiar with SYN flooding. Basically, you try to exhaust the TCP backlog. You know, early implementations, you know, SunOS had, you know, 4 or 8, something small like that. No big deal. Established flooding, last act flooding. These are in there's a good white paper by BindView called the NAPTHA attacks, and there's a couple little tools here, the SRVR, and that you can use to do these things, and particularly against some, you know, TCP-based or TCP protocols that use encryption, you can sometimes do some interesting things. But we really didn't find, I mean, the results were kind of disappointing or good, I don't know, depending on what your perspective is. But there wasn't really the negative impact of these attacks that we felt there could be. So, you know, with SYN flooding, I mean, it was actually harder because there was a lot of talk about how easy it is to basically SYN flood port 179 on a router, and it's actually not the case, particularly if the session is already established, because in most cases they're just reset and they're not. It's not going to the SYN receive state, so you're not blocking any new connection attempts. Now, if you were able to spoof the SYN from an established peer and the session were not already established, we were able to, you know, prevent new sessions from being renegotiated by basically hitting one side of the conversation. So basically, you're gagging one peer and you're forcing that peer that's under attack to negotiate the session with the other peer. Because BGP is weird because on both peers listens on 179, on both peers it tries to connect to the other router. So whoever gets it first ends up being the client. So if you wanted to do a real attack against BGP using a classical SYN flood, you would have to basically hit both sides of the both peers, and the sessions weren't already established. Now, BGP is something these sessions are up for a very long period of time, and they're almost always established. So low risk here. So I've already talked about that. Really not too much with TCP resource exhaustion. So I'll pass it over to Sean for TCP sequence number attacks.
All right. So the whole TCP reset thing and sequence number guessing was one of the things we really wanted to make sure we addressed in our testing, because like I was saying earlier, a lot of the theoretical vulnerabilities that had been published were based around the idea that it's relatively trivial to spoof TCP messages as a blind attacker. And I don't know if any of you have tried to do this in the real world, but we found it's actually quite a bit harder than easy. The reason why is, first off, as many of you probably know, to get a TCP reset to work, you first have to get the 4-tuple right? You need the right source IP, dest IP, source port, and destination port. But then you need the sequence number to be right. And the sequence number is a 32-bit number, right? The same size as the entire IPv4 internet. So it's sort of like trying to guess somebody's IP address on the internet at large and having, no information to go on. So the question is, don't you have to just be within the window? And the testing that we did, and again, the implementations is going to vary based on how close you need to be. But you need to be pretty darn close in a range of 4 billion. Even if you need to be within a couple of hundred, it's still a huge range. So the question is, do we test ICMP port unreachable messages?
Yeah.
Okay. I'd like to talk to you about that afterwards. We didn't do anything with ICMP testing at all, and what we did. So what we did was we wrote a basic tool to do this. TCP kill exists, and that's really easy to use already. But what we wanted to do is write a tool that would allow the sequence number guessing to work. If you see here, this is TTT, which is one of the tools you can download. And it's got a Nemesis-like configuration. You can basically go in and specify the sequence number pretty easily in order to cause the reset, assuming you have access to the sequence number. So the thing we found, though, is even assuming you're able to get the TCP reset to work, 50 seconds later, the peer comes back up in our test network. If you have a heavily loaded BGP network, it might take a couple of minutes before the peer comes back up, but it's not going to be a very long time. There's been some research in the past from Tim Newsham and others talking about TCP initial sequence number selection and how some of that is flawed. We didn't repeat any of those tests. That research has been out for several years now, so we're hoping that all the implementations have fixed this problem with varying degrees of success. We did find, though, that in both of the methods that we saw to do TCP, basically with these kinds of attacks, you're trying to narrow down the amount of sequence numbers that you need to guess. In both of these attacks, you needed to have a large seed of initial sequence numbers, such as by sending a bunch of SYNs to the telnet port and measuring all those initial sequence numbers that come back. If you keep doing that over and over and over again, you start to be able to potentially predict what the next sequence number is going to be. But if you're implementing best practices properly on your router, there should be no way you can implement or initiate a TCP communication to one of these routers, which makes that seed data impossible. So in all the testing we found that this is a very, very difficult thing to try to do. We also found that you also need to get the source port right? So if implementations were to move towards a pseudo-random source port, and many of them don't today, then that essentially adds another 16 bits to the number space you have to go to. So you go from 2 to the 32, 2 to the 48, in terms of the number space you've got to guess. Okay, so we said, all right, theoretically, let's just look at the math behind this. If we were able to generate 1 million packets per second on the wire, and we had a link that was able to deal with 1 million packets per second, it would take about 30 minutes just to guess a single sequence number, that single 32-bit number, assuming about halfway through it gets it right. And there may be some things you can do to narrow that window down, but it's going to be a large number. The tool we generated and optimized in C, we were able to generate 62,000 packets per second. So that bumps it to about 9 hours. Now, sure, there are different things you could do. You could do some kind of a distributed .NET kind of a thing where you have a whole bunch of machines trying to do this at once, and you distribute chunks of the sequence number space to try and guess. But if everybody's doing that at 62,000 packets per second, you have other problems on your router. right? You've got link saturation, you've got packet loss, you've got all kinds of other things going on well before any sequence number gets reset. Now, also, as Matt was saying, since either side is just as likely to initiate communication on port 179, you have to go after both sides because you're not sure which side is 179 as a blind attacker. So that essentially doubles everything you've got to do. And then, just for fun, we said, all right, if people were to go to pseudo-random source ports, that makes this really, really nasty, and you start going into, centuries to try and guess this stuff. So again, the walkaway is these kinds of attacks are going to be very, very high in packet per second count. The larger ISPs are going to notice it because they're probably spending a lot more time watching this stuff, and the smaller ISPs are going to notice it because their link sizes are smaller, and you probably flooded their link, and now all of their customers can't get out on the wire, so they're going to call and want to know what's going on. Okay, but again, this all goes away if you're doing our best practices right. So RFC 2827, if you're unfamiliar with it, how many people are familiar with it, by the way? Ingress filtering, anti-spoof RFC. Basically, it says, if I own the, 10, I wouldn't own the 10. Let's say I own the 11 network, the Class A. I should set myself up so that nobody can send packets to me with a source address of the 11 network, because that's my network, and that must mean somebody's trying to spoof me. Well, as an ISP, if I were to set that up so that nobody can send packets to me if I own the 11 network, I could prevent people from trying to communicate with me, prevent people from doing any of this TCP spoofing, and all this stuff goes away. So if everybody were to implement RFC 2827, IP spoofing, with the exception of the last octet of the subnet you're in, mostly goes away. But in the case of an ISP trying to prevent some of these BGP attacks or a large organization, just doing ingress filtering against BGP will solve a lot of these problems. Even if the BCPs weren't turned on, this is an awful lot of work at really high level of packet count to achieve 5 minutes of downtime, 50 seconds in a lightly loaded network. And then you need to keep doing this over and over again, because as soon as you reset the session, it comes right back up. Congratulations. The asymmetric nature of the internet, the larger the ISP, the more likely they are to have large numbers of asymmetric links all over the place. So you need to somehow coordinate this and get, hundreds of people around the world, thousands of people around the world to just keep doing this over and over again and figure out a way to narrow the sequence number down to be a manageable range of space that you have to go through. And again, link saturation is probably going to hit first. Question towards the back. Comment is, once you brought the link down, you can SYN flood both sides. Yeah, so if you were to get the reset to occur, and then at the same time somehow SYN flood both sides at the same time and get those packets out before the router reinitiates the session, you could cause some level of flooding. But in the testing that we did, it was never a permanent thing. It would just slow things down, and eventually they would be able to communicate. So, shifting gears into MD5. Those of you who are unfamiliar with BGP, it actually does have a security mechanism, not a particularly strong one, that's detailed in RFC 2385. This is the MD5 signature. It is not a BGP-specific function, although BGP is the only place where it's used. It's actually a TCP option, option 19, which essentially takes a bunch of the TCP fields, a bunch of the IP fields, zeroes out the checksum, adds in the payload, and then it concatenates that with whatever MD5 secret you define, and then creates an MD5 digest and puts that in option 19 and sends that along the wire. So if this side of the room is ISP A and this side of the room is ISP B, and you're trying to peer with one another, all you need to share is that individual secret in order to be able to communicate with one another. However, just like cracking password files with a dictionary attack, because an attacker is able to know everything except for the password itself, we found that you're able to essentially do a dictionary attack if you're able to get access to the packet on the wire. So we wrote a proof of concept tool called BGP Crack, which you can download. And what it does is it basically sits there and watches the wire, and or actually you do that via TCP dump, and then you essentially run BGP Crack against it, and it will sit there and churn through passwords until it matches the right MD5 signature that's the same as the one that was originally sent in the packet, and then it knows what the password is and it lets you know. So this is just trying to drive home the point that just because you're using MD5 for your routing protocols, it doesn't mean you're allowed to use the password of Cisco 123 or Cisco or password, right? Just because it's not sent doesn't mean it can't be determined. Particularly in large organizations where you might be running iBGP internally and somebody's able to do some kind of ARP spoofing or MAC flooding in order to get access to the packets. So it also can work with John the Ripper. So you can take John the Ripper's incremental mode, which I've got on the next slide, and I'll show you then. And there's an online mode as well, which we didn't do a heck of a lot of testing around. So let's do a quick demo. All right, so the first thing I want to do is start up Ethereal. All right, so while that's running, let me show you what the router config looks like. But basically, the way this lab is set up is there's three routers. Depending on the demo, we're gonna be using either one or the other two. And so in this case, we've got two routers that are talking to one another. Right now, they're running passwords. You can look at the configuration. Here's the BGP relevant part of the config. You can see, as Matt was alluding to earlier, you define neighbors. So you explicitly say with BGP who I'm going to be talking to by IP address and then by AS number. And then underneath that, you can see the password that we've set for that specific peer, and it's just a standard English word, gambling. So again, this is not necessarily good best practices. So do a show IP route. You can see it's pulling in the route from the other peer, and it's communicating, and everything is working fine with respect to BGP. So if we switch back over to Ethereal, it looks like we've gotten a few port 179 packets. We stop those. You can actually see, make this a little bigger. You can see that the signature is not in BGP. If I go down to the BGP information, let me go up to the keep alive. It's not in the BGP specific information down here. Scroll down. In the keep alive message at all, it's actually up in the TCP options. So there's TCP option 19. You can see the MD5 signature and pull that in. So that's the signature that it's using when it sends those packets out on the wire. And that's how it looks before you run this attack. All right. So if you exit out of the router, actually let me save this capture file. It's not going to do us much good. Just save over, call it capture. All right, so that's saved off. So these are the options here for BGP crack. There's a lot of options that are designed to make it more efficient if you're doing large-scale scanning. If you want to go through a whole bunch of different passwords, there's delays you can tell it only to go after the first frame that it finds. But by default, it's just going to basically pull in the PCAP file and just start going after any frame with option 19. So it's quite exciting to see. Let me tell you, you guys all have your fingers crossed here. All right, so you just basically specify -R for the capture file and -W for the words file. In this case, we get a really basic words file. If you were to write a words file to be tuned towards doing this kind of attacks, you'd put things like Cisco 123 and lots of instantiations of the word Cisco and Juniper and whatever else you want to do. So you run the attack, boom, it's done, right? Yay! So because there's only 3 segments, it basically pulled it into memory. The initial implementation that I wrote in Python wasn't nearly as fast, but when it was ported to C, it got a little faster. So there's the password, and you're pretty much done. So that's basically how this tool works. Any questions? Okay. Okay, and then just to point out the example here that I talked about with John, if you have John installed, there's an incremental mode that John can use, and you basically say how many characters you want it to check for the password. In this case, we used 6. So it's just going to go through and keep churning on passwords that are completely random. So in this example, you see here, it took 8 seconds to find the password domino in all caps, just using the regular words file. But then if I permuted that password to be D0M1N0 and ran that by basically piping the output from John into BGP crack, it took about 3.5 hours to get that, arguably pretty random password. If you were to, go to 8 characters, obviously this would take a heck of a lot more time. So countermeasure is very easy. Just choose good passwords. for your MD5, and this applies, this kind of a tool could apply to multiple routing protocols. It was only written for BGP. There's an IETF draft here that's linked at the end, which explains, how long your keys should probably be based on how long you're going to keep them before you change them to limit the ability for the attacker to go after the stuff. And this starts mattering a lot when you have an Ethernet peering point. Right now, there's a lot of cases with internet exchange providers where you have a lot of ISPs that are coming together and connecting to one another over like a big Ethernet switch, essentially. And so the requirement to do MD5 starts mattering a lot more there than over a private lease line between a customer and a provider, although they're beneficial in both cases. Okay, so the MD5 testing that we did, in addition to the proof of concept tool to figure out, is it possible to derive that password by just doing a dictionary attack, we wanted to see, can I use MD5 as an interesting denial of service attack? In the past, crypto protocols have allowed you to do an easier denial of service with a smaller number of packets, as is the case perhaps with Ike. So we wanted to see, is that same kind of thing possible? So we tried a bunch of different combinations, whether it was a valid BGP or valid BGP peer, invalid BGP peer, whether it was established or not established, whether the password was right or wrong. And we would just flood a lot of this MD5 stuff using this TTT tool. So 2 results we found: drop silently or reset. Everybody who dropped silently seemed to have a lower CPU impact. And in worst case, we found that using MD5 and doing SYN flooding, if the peer, if no session had been established, we got about 70% utilization. But what that doesn't show is that the router with just a regular SYN flood, because we weren't using 12,000s for all of our testing, was at about 60% utilization with just a regular SYN flood without any MD5. So it's really an incremental of 10, 12%, which didn't seem like it would be all that useful for an attacker to try to exploit. And then it dropped even lower if the session had already been established. The order of processing, though, did impact the results. So we found some implementations which, when you tried to test them over MD5, they would check to see if the MD5 signature was right before they checked to see if any of the other TCP information was correct, which is bad, right? What you should be doing is checking to make sure your IP addresses and port numbers and sequence numbers are right, the basic stuff that doesn't require any crypto, and then run the MD5 signature assuming everything is correct. So that's certainly something you may want to check and recommend to your vendor if your particular implementation happens to do this in the backwards order. And then again, the TCP behavior the different things that we found when we were doing the TCP testing definitely impacted the results. So something that was already fairly susceptible to a SYN flood, we're still just susceptible to a SYN flood with MD5 afterwards. The question is, did they think it was a good packet if the MD5 signature was correct? No, they didn't. So after they checked the MD5 signature, they would then go to make sure that all the rest of the TCP stuff is. It's just kind of a backwards order, not the most efficient way to do the testing. Okay, so now I'm going to turn it over to Matt, who's going to talk about update flooding and do a sexy demo.
Yeah, our 1750 is going to be simulating a core router. It's got a 48 megahertz processor and 48 megs of RAM, so we can definitely have the entire internet routing tables here. So responding to that earlier question about ICMP port unreachable, I haven't tested that stuff for a while, but if I recall, most modern operating systems, I don't know if you put Windows as a modern operating system, ignore that. So we did not test BGP, but I remember in the past testing other iOS TCP applications, and by sending the port unreachable, you were not able to tear down the session. But that's a good point for being comprehensive. So basically, assuming, and this is probably assuming a lot, assuming somehow you were able to complete your three-way handshake, get a valid open, and start sending updates to a router. We just wanted to see what you could do by flooding large numbers of update messages. So basically I wrote a little silly Python script that manually goes through and initiates a BGP session and starts sending routes to see how long it takes for the router to crash, the CPU to get exhausted, for it to stop accepting routes, for it to override existing routes, or things like that. So I'll show you what happens on this super powerful 1750 here. So, Only the best for y'all.
Only the best that would fit in our carry-on.
Okay, so simple pi, if I can spell here. Pi update, target the router, and then specify my autonomous system number, and we should see the peer come up. So basically, at this point, what I do is I'm manually establishing a BGP session. It brings up the route, and we should, if I go down here, tell I'm definitely using poor passwords here. So we've established a session, and what I'm going to do is one thing I've found is that you can't send more than 1,000 routes at once, so you have to split those up. So I'll do 1,500. So that should, you'll see that it splits it up. So very exciting, sends a couple of updates. So just to prove that now we have 1,500 routes. So we start upping the ante. Now over 10,000 and continues, and console becomes somewhat unresponsive. Now if we go to 100,000. It came up now. And it's getting kind of sluggish on the console. And big surprise, we ran out of memory. Really, that's not a bug, it's a feature. So, okay, the point of this kind of silly demo is that the different implementations responded differently to this sort of attack, if you can call it attack. I consider this almost kind of like dev testing, so I really didn't even want to do it. So, but anyway. So what happened on different implementations was we saw a wide variety, and we were shooting for pretty much comparable hardware platforms. There were, at the rate at which new routes could be accepted, that varied even on comparable platforms. The number of routes that could be accepted, just the maximum number of routes, really varied as well. And then probably the most important was what happens when you hit your max. Let's say you only accept 200,000 routes. Do you start overriding existing routes? Do you not allow any new routes? Or as we saw in the case of iOS, you basically terminate the process and renegotiate. And the theory behind why you would want to terminate the process is you want the router to be in a known state. So it's better to kill the process and renegotiate the sessions than to accept all of these routes and put the router in an unstable state. So Sean's going to move on and talk about the TCP hijacking.
All right, so TCP hijacking. So assuming the ability to guess the sequence number, which as we talked about earlier is not the easiest thing in the world to do, let's assume that the attacker had some method to do that, whether they're inline or through some other method. How easy is it to send this magic single spoofed message? Because ideally, if you have a BGP peer that's already set up, I can send a single packet as a BGP update. If I get all the fields right, I can cause a route to be picked up by the victim and then propagated throughout the internet. So we wanted to test to see how that would work. Well, what we found is we wrote a tool to do that, which is again available on the website. And instead of trying to guess the sequence number, we just make it only work in line. So it just sits there in line and it watches for like BGP keep alive. And once it sees the BGP keep alive, it can sync to the TCP session, knows what the sequence number is, and then it can send the update. You'll see that in a demo here. But as soon as that update is sent, what immediately happens is those sequence numbers have been stepped on, right? Because I sent in a spoofed BGP update, and now the sequence numbers between the client and the server, the real client and the server, get out of sync. So they run into an axe storm. If you want to look it up on your Stevens, basically it just starts storming for about 5 minutes. You'll see it go by on the TCP dump. Just all kinds of crap streaming by. Meanwhile, the BGP session is fine because, again, this is happening at the TCP layer. And all that information will be propagated up. Whatever update you send will be propagated to any other routers that are listening. However, again, as soon as that ACK storm is resolved, the session is reset and rebuilt, meaning that route that you inserted will no longer be valid. So again, it takes about 5 minutes to resolve that ACK storm.
And there are ways of getting out.
Yeah. So you're right. So we didn't do a lot of testing to figure out ways to gracefully back out to make that ACK storm not happen, to resync the sessions. Obviously, if you're doing something like ARP spoofing, if you're in line, you can do a lot to make sure the sequence numbers don't get messed up. But if you're just a blind attacker several hops away, it's pretty difficult to get those sequence numbers to resync. All right. So let's do a quick demo here. Let me start up TCP dump. So what we're going to need to do is we're going to need to start this up because you're going to need to know what the port number is in order to send this hijack out. So while that's running, so there's a couple of tools here that you need to use to do this. The TCP hijack tool that we're releasing isn't BGP specific. Essentially, it's dirt simple, right? It just watches for a TCP communication to go by on the wire that matches what you configure, and then once it's synced to it, it'll send whatever binary payload you identify off to the victim. So we wrote a little utility called BGP update create, which builds the binary payload for the BGP update. So you can see it's only got a couple of parameters. So we just say BGP update create. In this case, the AS number doesn't matter. The next hop has to be the hop of the server that you're spoofing in order for this to work. So in this case, we're going to send it to .200, which is the victim. And then we'll use the desknet, I don't know, 69.0.0.0/8. So we'll send the class A. And if I just hit enter, it's just going to write the binary payload as standard out. So I need to redirect it, call it test update. Now I've got the test update file, and now I can run the TCP hijack. Those are the command line options. Now I need to go back over to my TCP dump to look for the keep lives. So I can see that 200 looks like he's the client in this particular situation. So he's got port 11,001, and 100 is the one who's active on the 179 listener. So because I'm going after 200, I need to send it on port 11,001. So I go back over here, I'm going to say TCP hijack, -C, the client, which is the client that I'm spoofing, to the server, which is the victim. Then the port, in this case, is 11,001. And then the payload file is test update. So I hit enter, and if everything works right, it's going to take a few seconds because, again, it's waiting for that it's waiting for that BGP keep alive to go by on the wire. Once it sees the BGP keep alive, it'll know the sequence number, and it will be able to sync to that conversation and send it out. So far it still hasn't synced yet.
Has anybody seen the BGP plugin for Ethercast? Look at the source code. It's kind of amusing. It's not trying to track MD authentication.
All right. And we're waiting. There we go. Okay, we're synced to the TCP conversation. It sends the payload, prepare for network meltdown. And by network meltdown, I mean this. Yay, there's your ACK storm, right? So, however, while this ACK storm is happening, I can telnet into one of the routers, in this case the victim, and do a show IP route. And there's that 69 network that we sent. So while that ACK storm is resolving for the next 5 minutes, that route will be picked up, and that route will be propagated to all other peers that are connected to that peer. So that route will get into the network. But again, preconditions for this attack is you got to get the TCP sequence number stuff right, or you got to be in line, in which case the TCP hijack tool will work by itself.
And
There's no MD5.
Right, this is also not assuming MD5, good point. So if you had MD5 turned on, I guess you could probably do some Frankenstein work building on what we're releasing to take the BGP crack tool and the TTT tool, but we decided, most people, to be honest, how many people here are using TCP MD5 for BGP? Yeah, okay. That's right, I saw 0 hands. So most people aren't using it because of the key management issue, right? It's really painful to manage pre-shared keys on all these routers, so a lot of people just plain don't do it. So we thought, sort of a declining returns to spend too much time trying to go after MD5. All right, and then there's some simple things you can do. Again, just ARP spoofing. We're not going to spend any time on. One thing that was interesting to note, though, is if you have a victim who's multi-homed, meaning he's peering to multiple peers, one of the problems with ARP spoofing is you want to make sure the rest of the communication continues to work. So if instead you only spoof one of the victim's peers, you can basically leave that up and running, and then be able to send whatever spoof traffic you want over the spoof peering, while the valid peer will continue to send all the information. So that's the TCP hijack tool. And now Matt's going to get into protocol fuzzing.
How many of y'all have heard of the term fuzzing? It's a pretty old term. First kind of appeared back in the 80s. I think some research at the University of Wisconsin, primarily on the host side, basically sending all sorts of input to Unix environment variables, command line arguments, things like that. I won't claim that fuzzing is any sort of panacea, but I'll tell you one thing, it scares a lot of people. I could tell you some stories, but I can't. So
We're not releasing the tool, so
yeah, the bottom line is not able to release this tool. So basically, how many of you have heard of ISIC? How many have used ISIC to crash a network device or an application? Okay. Basically, the goal of this tool called PIF, Protocol Independent Fuzzer, was to kind of go beyond the functionality of ISIC. ISIC is really cool. It was written by Mike Franz, and I think came out in '99. Provides about a half a dozen tools: eSIC, ISIC, TCP-SIC, UDP-SIC. UDP-SIC can be useful if you try that against your IKE implementations. I think they probably fixed most of the things now, but never can tell. But it's pretty crude. Basically, it gives you some control over IP options, TCP options, whether or not the checksums are valid. But the payload, whether it's an IP payload or like a UDP payload, it just generates random crap. Now it's not really crypto random. It just basically uses the process ID to run it to the as the seed. But and you can do a few little things to make it a little bit better. If you add a few lines to ISIC, you can specify a IP protocol number. So then now I could get some granularity. I can say, well, maybe I want to go after IP protocol 50 and 51, ESP and AH, or maybe I want to go after try some malformed GRE. But really, it's not giving you the functionality that you need to send those malformed payloads deeper into the packet. So the goal of PIF was to come up with a simple way of describing a large number of primarily binary protocols, and I use BGP and IKE as the primary test protocols, so that you could basically, you describe the protocols, you run the script prompts you for some possible field values, and then it generates test cases. So this way you can have much greater control over which fields you want to try to send invalid data to. And the theory is that the greater or the deeper into the packet that you're able to inject invalid data, the greater you're going to expose possible points in the code where things could go wrong. So basically what I ended up writing is it's 1700 lines Python. Came up with this simple flat file format, and I'll go through a demo and show you what it looks like. But a simple way of describing the protocol. Didn't want to use anything like BNF or ASN1 like some folks would like to do. Describe the fields of the protocol, have a user input module, which is basically a interactive script that asks you what fields you want to use, generate the messages, and then the messages end up in just standard binary format, just like the SNMP Protos tests or SSH Shredder test suites. That's pretty much the standard way. And then you can use whatever you want to inject them. So this is just what it looks like for BGP if you want to generate some messages, and I'll do this. So this is the nice management slide I came up with. So lines and boxes and pictures, great. Okay, so you have the protocol description language. You look at your sniffer traces. You look at the specs, and you come up with a simple way. You come up with a definition. Now, one of the things that I wanted this to do is, let's say I only wanted to describe the first few fields in a protocol. I didn't want to define the complete protocol. That's fine. It basically takes what you've got, and then the rest of it just generates crap. So then you generate you run the PDLs through the engine, generates test cases, then you fire it on the network, and hopefully it'll cause some damage and cause your router to crash and do all sorts of nasty things, depending on your perspective. Okay, so basically, PDF directory, PDL, has a set of protocols. We'll go into BGP. And the way it works is each file is essentially a group of fields that go together. So this is the simple generic BGP header that you've seen when we opened up Ethereum. So the first column is basically a tag descriptor. The F would be for fixed values, things that always change, that don't change. For example, at the beginning of every BGP message, there's a 128-bit, I think that's 16 bytes of all Fs. So that's always has to be there in order for it to be a valid message. Next field, length field. Now, one of the interesting things about protocols is there are probably about half a dozen different ways of calculating length. So I had to write little functions which properly calculate length. Now, why do I want to properly calculate length? Because some implementations, if they look at the top here field and it's an invalid length, they just drop it. So they don't do anything else. So you need to be able to build valid lengths. And then the third field there is basically a type field, and I can specify the different BGP option types. Now, there's basically 4 or 5, and you can use the hexadecimal value, or you can use the standard name. The last field is an action, A or action field, and it basically, based on the value of the previous field, it will go to the next block. So assuming we're doing it open, it goes to the open fields. So version number, BGP version 4, your autonomous system number, 16 bits for the whole time, etc. And then you can append options onto this. So, if you want to go deep into the packet, you could chain together 6 or 7 different files, and it can get kind of hairy trying to write these things up. BGP is easy compared to some of the stuff in IKE. So basically how this works is you're within the directory of the protocol that you want to generate messages. And I'll say pip, BGP, build, fuzz, and then this neat feature called backtrace. So basically what this is going to do is it's going to read in the first file, and I'm going to say, well, I want it to do a valid length, and I want it to be an open. And based on the decisions that you get, it will make certain choices, and it will piece together your different messages in the protocol. And I want to use my autonomous system number, and that I'll just do random. And then one of the cool things is, if you ever stop and you just hit a return, that just means fuzz the rest. So the rest of it's crap. So if you just want to quickly start generating messages, just fill in a few fields, hit return, and then you're ready to go. So don't need to enter a file name. So these are the nasty Python dictionaries. Dictionaries of dictionaries of dictionaries. Very, very messy. I probably couldn't tell you what they mean now. So now it says, well, these are the fields that we've processed. It populates them. And so we have the last valid field is the BGP ID. And then there's the rest of it is the fuzz load. So I was going to add so you can have multiple embedded fuzz loads, but I didn't get around to that yet. So for this fuzz load, I'll specify a minimum of 0 because, as you all know, you need to test 0-length messages because they do crash things. But historically, there have been a lot of protocols that have issues with that. So basically what this is going to do is, using this backtrace feature, I specify deep into the message, almost a complete message that I want to build, and it starts popping off each field. So it basically moves the fuzz load more shallow to the front end of the packet. And I'll show you what it looks like in just a second. So 10 messages. Okay, so basically what it's doing, and you'll see this number now, it's 6, 5, and it's going shallower into the BGP message, now to the marker, and now we just have a fuzz load. So basically it creates directories in here. So if we go to fuzz load, you'll just see this is complete random. There's no valid marker there. So if we go BGP length, so there it starts to look more like a real message. And then within each file, it just tells you what to do there. So to kind of illustrate what these look like on the network, let's see, I'll open up Ethereal, and instead of having to have an actual existing implementation running when I was doing all the development, I just wrote a little simple script that opens up the netcat listener just because I just want to see it on the wire and make sure that it gets decoded by Ethereal. So basically I'll go just type trace 179, and it's just a really stupid shell script that opens up ncat-l and then pipes it with another ncat. So you can see that it's building up TCP. So this one is actually an unknown message type. It has a valid marker, the length is valid, so it's a message type 45, so it doesn't know what that is. So theoretically you might want to test an implementation to see how it responds to that. And then you basically can do the same thing with other, let me go here. And I'll show you what it looks like on the router. And I did write some scripts to automate sending large numbers of test cases. It's probably not as automated as if I were going to be doing this full time, because it can be kind of painful. Okay, so what I can do is, and I really hope this doesn't reboot the router. I really hope it doesn't, because I'm going to get fired if I do. It's a joke. Maybe. So, it's one of these. So. Okay, so basically what I'm going to do is I'm going to cat the file 192.6.2.225, specified port 790. Okay, good, I got a response. That means that it's sent a notification back. So I'll look back, and so basically it shows you those messages right there, and you would use that to do debugging as you go through exposing various fields to determine whether or not there were issues in that protocol. So that's basically how I generated these test cases. Came up with about 800 BGP open test cases. Those of you that are familiar with Protos know that that's significantly less. Protos had 30, 40,000 test cases. They chose a slightly different approach, more of a permutation through all possible packets. It would be interesting to see if this approach, which is a little more efficient, has the same coverage in terms of number of vulnerabilities. So generate full screen. And then I also generated fewer, okay, so this is just another shot of what it looks like. We've got it in the slides. And then I did the same thing for updated. I didn't do as many updates because I didn't write out the complete PDL for the updates because it starts to get pretty hairy and I would have had to do a significant modification of the code. And also, since basically in order to send an update, you have to negotiate a true session. You have to have a valid IP and a valid AS number. So from a risk perspective, do the opens first. So total about 1,200 test cases. In terms of the response, came up with 4 unique flaws in 4 different implementations. I was actually expecting to find more. I feel pretty confident about the open test cases in terms of exercising the various fields. There's probably some more room in terms of the BGP options that are used for the open for negotiating, MPLS or various routing extensions, because as we know, options always have lots of potential for mischief. So 3 of the 4 vulnerabilities had to have a valid AS, and only 1 of these could you do remote, and these are remote compromise. I'll keep it as ambiguous as that. So like I said, need more comprehensive update testing. One of the questions I got when presented some of this material at NANOG was, have you tested the system-wide effects? So let's say I send an invalid update to one router, it's properly handled by that, but it gets passed on to another router, which then cannot handle it and crashes. No, I didn't do any of that. I was just focusing on a single router. So there is some more potential work that needs to be done in terms of invalid messages. And hopefully, assuming there's a cert advisory that comes out, maybe the test cases will go public, and maybe someone will find this idea interested enough to maybe do some work on this. So anyway, okay, so based on we did, looked at 7 implementations, the TCP stuff, the BGP stuff, we saw a variety of responses, and one of the things was the logging. Some of these implementations basically gave you nothing to go on. Some of them were extremely verbose in terms of the types of malformed messages that you were sending, and so that I would recommend that if you're looking at identifying potential attacks, obviously more verbose logging and configurable logging is a nice thing. Aggressive rejection early into the state. So the best case would be I send a SYN from a non-peer and there's no response, or it doesn't, or it resets it. Does not allow anything to get to the SYN receive state. It certainly does not process any BGP open from an unconfigured peer. That's the best case. Source port randomization, we talked about the issues with TCP sequence number randomization. Timeouts, we found, made it more difficult to do the testing because we had to clear them out. And there's also a work within the IETF to require that BGP accept a TTL of 255 or 254 to help minimize the impact of spoofing attacks. So I'll move on to Mr. Best Practices right here, Sean Convery.
All right. So in the last 15 minutes here, let's kind of put this all together. This is the test network that we built out in the lab. Again, not necessarily representative of the internet as a whole, but we tried to make something wide enough that we would actually be able to see some interesting results. And again, our goal here was to see, given all these attacks that we talked about, how easy are they to run against the network implementing best practices, and how easy are they to run against the network not implementing best practices, and does the location on the wire, whether you're blind or non-blind, matter? These are the best practices that we use. We based them off of Rob Thomas's hardening template, which is essentially the same as the ISP Essentials template. We made some additions, though, in red for internet exchange providers where you're doing Ethernet-based peering, things like static ARP entries, static CAM entries, port security. A lot of the layer 2 stuff, which has been talked about before, starts mattering a lot in these environments. One of the interesting things to point out is similar to ingress filtering for spoofing, they have mechanisms to do ingress filtering for prefixes. So I can say if I'm an ISP and I'm peering with a customer who has the 57.27, CIDR block class B/16, I can set it up so that that's the only route I will accept from him. So that if that router somehow gets compromised and somebody just starts spewing crap, crap/32 routes, I can set prefix filters up to prevent that. So that's definitely a recommended best practice. And in many cases, it's the only thing that helps you when there's a compromised router. If I've got a compromised router, just like if I have a compromised web server, all bets are off in terms of what you can do with that compromised device. So, actually, I think I somehow skipped the slide. Sorry, guys. So, if we look before the best practices, backing up one, apologize. If you don't have any best practices at all, as a blind attacker, because of the sequence number guessing problem, most attacks are mostly impossible. You know, there's potentially some things you could do, but the pain involved is going to be such that an attacker isn't necessarily going to want to spend a lot of time in that space. And everything depends on getting access to a link with a BGP speaker on it or compromising a router. So those become really, really important as initial tests. As a non-blind attacker, there's a lot more you can do. I can reset sessions at will. I can insert routes, but again, that ACK storm is going to tear down the session after a few minutes. I can do peer hijacking with ARP spoofing. There's a lot more damage I can cause. And then finally, with a compromised router, I can do just about anything I want, which includes sending valid or invalid prefix information out. So if I want to modify the AS path of a BGP update so that, you know, maybe traffic is preferred through my ISP when it's not supposed to be, I can cause traffic to be redirected through my connection. So we talked about the best practices. If we have all those best practices implemented, the key ones become, for a blind attacker, RFC 2827. Again, the ingress filtering, anti-spoof RFC. If I do this right, I can stop all the TCP-based attacks that are happening from a remote blind attacker. And then if I have a BGP implementation that will SYNAC to 179, even if it's not a configured peer, I can do some work with BGP ACLs to basically limit who's allowed to talk on TCP port 179. So those become the two biggest hitters for a blind attacker. For a non-blind attacker, again, layer 2 best practices that we talked about before start mattering a lot. And then MD5. In an Ethernet exchange point, that becomes a lot more valuable than MD5 digest for BGP might be in a private peering relationship over a private lease line. And then the ingress and egress prefix filtering, which I talked about in the previous slide, that's going to limit the damage if there's a compromise. Same thing in a compromised router. That prefix filtering will allow me to prevent a lot of the update flooding from happening. Now, the closer you get to the core of the network, the harder it gets to be able to do that prefix filtering, because due to the asymmetric nature of the internet, it's more likely that you start receiving all kinds of different networks. So you can optionally set how big a prefix you'll accept. So you can set it up and say, I'm not going to allow anybody to advertise a /32 route, because that's a host route. I shouldn't get that. But I may say, let people advertise anything 27 bits or smaller, for example. Might be a best practice that somebody would implement. So, as we expected, a compromised router is the most beneficial thing that you can have as a BGP attacker. There are certainly lots of data that's shown that there's a lot of BGP routers that are able to be compromised or have been compromised. We'll show you some of the ISP scan data here in a couple of slides. But that doesn't necessarily mean we need to completely replace BGP as a result, right? I mean, I can compromise a web server, but that doesn't mean we need to throw out HTTP as a protocol. So we want to focus on the things that the attacker can do with a compromised router or without a compromised router, and try and fix those problems first with any modifications that we make to BGP. All right, so the active survey results. So the goal is we didn't want to intrusively test. There's a lot more work we could have done if we would have went very aggressive in the port scanning that we did of the ISP routers. If we went after and tried to log into these boxes, if we tried to establish peering relationships to the boxes, there's a lot more we could do, but having Cisco port scan you is probably not something real high on your list of happy things to have happen. So we tried to make this very, very benign and try and stay below the radar, although, because Matt basically had to stand up in front of Nanog and tell the ISP community, we just scanned you, sorry. And they were pretty good chaps about it. So the way we did it was we limited the scanning to only a single SYN. So this is going to result in the results being a little bit skewed, because if something got lost in transit, we're not going to do a retry, because we wanted, again, to keep this very, very light. So what we started with is we went to one of the route servers on the internet and got the entire internet routing table, which is about 120,000 routes. And then we took each one of those CIDR blocks and then created a host out of that CIDR block. So HP, for example, has the 15 network. So we took 15.0.0.0, we took those last 3 zeros and then randomized to create a source address or a destination address for our trace route. That we took those 120,000 routes and then traced to each of them using the tools that Mike Shipman developed for us. and basically built a huge database of all the various potential routers that we went after. We then lopped off a couple of hops at the front and the back to make sure we had BGP speakers, and then uniqued the list and pulled out RFC 1918 routers, which, believe it or not, there are RFC 1918 addressed routers in the core of the internet. You know, if you've ever had traceroute, you know, return a 10 network address and had trouble troubleshooting, you know, that's certainly why. Then we sent the TCP SYNs on port 22, 23, 80, and 179. We embedded a message into the payload saying that this wasn't some sort of you know, attack, and that if they wanted more information, they could contact us. Mike actually did get one response. I'm not going to say who, but let's just say I have a little bit more respect for the information security skills of our military. Actually, we were notified through the Cisco account manager. It was everything's okay now. We're all still employed, so. And we measured the response. You know, did they send a SYNAC? Did they reset? Did they give no response at all? And then the TCP 179s that did SYNAC, we then sent a BGP open to try and measure the response. Okay, so what do we find? Well, after we uniqued the list, we had about 115,000 routers that we went and scanned. Of those, 4,000 responded, over 4,000 responded with a SYNAC to BGP, 3,000 reset, and the vast majority, thankfully, gave no response, as you would expect them to. When we tried to send a BGP open to those 4,600 that sent SYNACs, we found in most cases we actually got a connect, just a TCP connect with no data, so we weren't able to establish any kind of BGP communication. But about 1,600 of them sent open notifications, some with authentication fail, and then some we got the cease message, which we didn't previously see in any of our testing. Some we got notification onlys where we got a cease message as well. So this information combined with the TCP information that Matt was talking about earlier in the presentation could probably use as a way to fingerprint BGP routers on the internet based on the responses that they give to some of these invalid or valid messages. That's something to be aware of. Now, again, you know, basic best practice for an ISP, you should not be allowing people to telnet or SSH or web to your routers from any arbitrary IP address. This is a basic best practice, so we figured if the ISP wasn't doing that, then there was no way they were doing prefix filtering or any of the more advanced best practices. So we found 6,300 responded on port 22, over almost 11,000 on port 23, which is pretty scary, and 5,500 had web servers running, which is never a good thing, you know, for your router if you've you know, ever followed any of the hardening templates for devices. And then we took that list and said, okay, how many of the routers of the 115,000 were reachable on at least one of those ports? And we found over almost 17,000 were reachable on at least one command and control port, which is 14.5% of all the routers we tested. So based on this data, and again, like we said, we skewed towards being sort of nice in our scanning, so the data is going to be a little bit inaccurate. You know, 15% of the routers out there are reachable on some kind of a command and control port, which isn't you know, good. So then we took a commercial tool that we purchased to unique that list and to give us information on country, just for fun, to kind of see what areas of the world might have the most susceptibility or to some of these attacks, or the best implementation of best practices. So we had lots of countries that either had 100% of their routers accessible on command and control or 0%, but we didn't include them because there were less than 10 routers in the country that we actually tested. Yeah, there was probably more than 10 routers in the whole country, but you know, only 10 that we tested. And then we came up with a list here. This is just showing you sort of the best, the average, and the worst. USA, because it has the vast majority of the routers, you'd expect it to be near the average, and it was. You know, anybody here from Maldives or Gibraltar? You know, excellent, very nicely done. 0%. So, and then you know, if you ever go to the Bahamas and you know you get tired of sitting on the beach, you know, probably most of the routers there would happily allow you to log in with the password of Cisco. So honorable mentions, actually, it's worthy of note, Spain, France, and Great Britain, which all had large numbers of routers, all did significantly better than the US and Canada in their implementation of best practices. All right, and then we'll give it over to Matt, and he'll wrap it up, and y'all can go on your way.
So fortunately, this ended on a sour note, because one of the painful and unusual things about this work was that as a security researcher, typically your job is to say that everything is horrible, the sky is falling, and things are really bad. So some of this work was kind of curious in that we were saying, oh, well, BGP isn't as bad as it really, as it could be, but I don't want to give the perception, or I want you to walk away that things are okay with internet routing. The goal of this work was to provide some more concrete data on where specifically the issues were. Where were the vulnerabilities? Was it through using BGP, or as we found that the greatest threat is obviously a compromised router. So if the greatest threats have nothing to do with the protocol itself, then maybe when you're devising solutions, you shouldn't move so quickly to implementing solutions that will require massive upgrades and widespread deployment of PKI, etc. Now I'm not disparaging these SBGP or SOBGP, but it's important to know where the real risks are. And based on the testing that we did, it's just the basic common sense stuff, and it's harder to actually do things with BGP itself unless you're able to somehow compromise that link. So simple things that we thought would be fairly easy, some of the TCP attacks, proved to be harder than we would suspect. So you have to, someone asked, well, if I reset the link and then I quickly SYN flood it before the links are established again, then you're able to do something with SYN flood. So it proves to be harder than what many folks were talking about. Now, and kind of the bottom line is that, the way I see it is if you're an attacker and you have a specific objective, you will choose you're not trying to choose the most elegant or the best attack that will get you a nice black hat presentation. You will choose the path of least resistance. So given the data on the large numbers of owned routers out there and the large numbers of routers with default passwords, and this correlates with what we saw in terms of the admin ports, the best way to altering the internet routing infrastructure is to compromise a router and do it that way. So, in terms of other things, encourage folks to do testing. I mean, there's never enough time to do security testing. Vendors have to do their jobs, independent researchers need to do their jobs, academics, customers, if they have the ability to do testing of devices. So that's one thing. The testing that we did was by no means 100%. I'm sure there are some things we missed. The goal is this, because there was such a scarcity of information on testing of actual devices versus more theoretical academic work, was to just put some information and some techniques and some methodology and some tools out there so folks could extend and test more devices, fill in some gaps because there are probably some gaps. BCPs, best common practices. You hear it over and over again, but people don't do them. Also, and I found this to be true in some other areas such as SCADA protocols. There are a lot of folks that are just literally out there saying the sky is falling, things are completely insecure. Makes folks be a little more specific. What are the specific problems? Where are the vulnerabilities? Because we're not in this, security is not all or nothing. And, there will be, within, probably the most aggressive estimates, 18 months to 24 months, there will be secure versions of BGP that reach the standards form, but they're not going to be here anytime soon. So you need to use the best practices. You need to tighten the vendor's implementations, because there are a lot of little things that you can do to minimize most of the attacks. So, and like I said, there's more test cases because we were not comprehensive, and based on the responses that we got from scanning ISP routers, there are definitely some implementations that we did not get to test. So, and there's a whole bunch of references. So, I guess maybe a few questions.
I think we're done.
We're done. Okay, we'll be around if anybody wants to give us feedback or argue with us or whatever.